I'm going to be talking about a branch of combinatorics called computational combinatorics. And I'm going to be talking about a specific type of search algorithm in that branch. And almost everything I talk about is made by the student Eric Stoley, who actually used to be a teacher here, many 10, 15 years ago. And then he went to Iowa, and now he's at Microsoft working on making Git fast, which is cool. I don't know. He's a graph theorist. Nice guy. Anyway, 4 sections. Start with motivation. So when we generate objects, or just when we do combinatorics in general, we want to count things. That's what we're doing, is we're counting sets, or counting objects, counting how many of them are there, right? And we don't want to not count any of them. We don't want to double count any, right? We don't want to count any more than we need to. So how do we actually do that? We started some sort of base object, and we'll make this a little bit more specific in a second. We add things to it, and then we remove any symmetries, right? We get rid of any, we're going to call these isomorphisms for most of the compensation that we have, right? So how do you find all permutations, for example? What do you start at? You're going to start at the empty set, right? Or the empty list. And then to the empty list, you're going to add just the next step, right? The next sort of permutation, which in this case, you're going to add 1, 2, 3. You're going to have 3 starting objects, 1, 2, and 3. And you continue this process, adding, to 1, you add 1, 2, 2, you 1, 3, 2, 1, so on. This makes sense, right? So you do permutations. Eventually, you get an answer. And as we're generating this, we don't have to worry about symmetries or isomorphisms, right? We don't have to worry about are these 2 objects the same? Because that's not really it's not really a thing. What happens if we do this with subsets, right? If you do this exact same process where you started with the empty set or an empty list of sets, and then you start adding objects to it, what breaks? What goes wrong? Why are these are not all the subsets, right? If you took all of these, what have we done? We've counted 1, 2, and then also 2, 1, right? These are the same subset for the same object. So when we're counting subsets, we need to keep track of isomorphisms. We need to get rid of them, right? And did I lose it? I lost it. Oh, it's connected to your. Okay. Anyway, so we call this general process of adding things to an element. We call this an augmentation. And in general, and we're going to talk about graphs now because this is a little bit more interesting when we talk about graphs, as opposed to subsets or permutations or whatever. We can take a base object, we can take any object, and we can add things to it. We call this set of augmentations, this A of X. We call this the set of all of the things, all of the possibilities when you're starting with some object that you go up to. And similarly, we can take objects away, right? So we can start from a base object and we can remove things from it, and we get a set of similar objects that we call the deletions of that object, right? And it should be kind of obvious that these two are these two can be related, because the augmentation of some object is going to be the deletion of some other object. So there should be some bijection between them, right? If you take a graph with a node in it, you add a node, now you've got 2 nodes in a graph. That's the same as taking a graph with 2 nodes, or taking a graph with 3 nodes and removing a node from it, right? Right. So there should be some sort of we call this a natural bijection, which these are pretty not this bijection, not this and this, but A of X and some other objects. Deletions should have some sort of bijection between them. And we can talk about this in terms of graphs, right? This is a pretty cool diagram where this is a set of 3 nodes all connected. And the augmentations here, the way these are described is if a node is white, we're going to connect a node, we're going to add a node, and we're going to connect it to the white nodes. And if a node is black, we just leave it alone. So this augmentation is we're taking this 3 node and we're adding a node to the top there, connected to that top one, right? And we're doing that for everything. And similarly, deletions we'll say are when we we highlight something red, and that means we're removing it, right? So these are all the deletions of this 3 connected set. And this is sort of what I was highlighting, is that this augmentation, this set of augmentations, is also the set of deletions for some other node, right? Does that make sense? There's an issue here though, right? If we wanted to count things going about this method, that graph and that graph are the same graph, right? They're isomorphic. Does that make sense to everybody? How those two are the same thing? So that's not great. I just realized Zoom can't see the pointer. That's probably fine. So when we just generate augmentations, we don't we have to worry about symmetries, right? They won't be symmetric, things will get messy. So how do we get rid of those symmetries, right? What if we, at every step, as we're generating augmentations to like a graph, for example, we filter out all the local isomorphisms? That doesn't work either, unfortunately. This is a counterexample that you can think about. Here we have one graph, and we go to this graph over here, and this bottom graph. These two graphs are not isomorphic, right? So you can think about now, like we've got like 20 computers. On one computer, we compute this, and then we tell two different computers to start thinking about these. Both of them will get to this same object at some point, even though locally these two aren't isomorphic. These two aren't isomorphic. Just making augmentations to the same graph, even though at each step they're not isomorphic, they might eventually converge to an isomorphic object, right? So it would be really nice if you could just like rule out local things and then we're done, because then we can parallelize this, right? That's kind of the goal of what we're talking about today, is we want to be able to do like searches on graphs, searches on various things, and we want them to be able to be parallelized. Because to go about doing this, you kind of have to you have to keep track of every single like graph that you've got. And at every computer, at every stage, you have to compare all the graphs, make sure they're not isomorphic, and then remove them, right? That's not, I mean, like that's slow. Although what we talk about is still pretty slow. This is a hard problem. If you have like solutions to this, you'll probably make a lot of money. So we have a way to label, yeah.
Can you go over what exactly is the hard problem?
Yes, the hard problem is just generating graphs, right? And making sure that you're only generating them once, right? Like if we started at a node of 2, started adding nodes to it, eventually every split we do would get to the same 5 node. So you'd go from 2, and that would expand to like all graphs of size 3, which is exponentially larger. That would expand to all graphs of size 4, and all graphs of size 5. And you'd have to check equality every time you do that. And that's just like exponents. I don't even want to think about how big that gets. I think it's like 2 to the it's a huge number. Just even for 5, it's a huge number, like the number of graphs, even for 5. All of the like numbers we talk about today will be pretty small. I think there's an example at the end that we've only been able to show for all graphs up to size 13, which is not like graphs with you get bigger graphs like homework assignments. Anyway. So we're going to assume we have a way to like check that graphs are isomorphic, right? This is a slow process, but it exists. There's software that solves this. The most like famous software is called Naughty, Nauty. I don't remember what it stands for. But essentially what it does is it takes each graph and it gives it a labeling. So if you've got like an unlabeled graph, like all the vertices don't have names on them, and it literally gives them all names. And what Naughty promises is if you give it 2 graphs that are isomorphic to each other, it'll give them the same name. And that's all it does. And then you can just check if 2 graphs names are the same, and that means they're isomorphic. It's a pretty simple, like literally, it's like a C++ library. It literally gives you like a standard string. But the issue is, and it's a slow process, but it works, right? It's what we're building off of. The issue is, as we're getting to bigger and bigger graphs, the amount of graphs we have to compare to like make sure we're not looking at duplicates kind of explodes, right? So that's what happens if we like started a smaller graph and like work upwards, right? What if we worked downwards somehow? So yeah, like I was saying, in the process of checking the 2 graphs are isomorphic, all the like common software that like tells you that's true also generates a label for the graph. It gives you like you can literally think of it as like if you've got like a graph with 4 nodes, it like gives one of them the name A, gives one of them the name B, C, D, right? Like it literally gives them names. And we call like that labeling, we can like think of it as a function where if 2 graphs are isomorphic, this like equals with the tilde over it is the isomorphic sign. If 2 graphs are isomorphic, then their name, that canonical label, will be the same. And so like what's an obvious like labeling for subsets, for example? Did I have an answer to this? No, I didn't, but it's in here. An obvious labeling for subsets, for example, is to just like sort them in lexicographic order, right? So that way, when we had the problem earlier, where we had like 1, 2, and 2, 1, the correct name for that would just be 1, 2, right? Just things like that. Does that make sense so far? So then we get to sort of the key idea of like this graph search approach, which is canonical deletions. So every single label that we've got, right? Like you've got a graph with like A, B, C, D labels or whatever. It's got a set of associated like augmentations and a set of associated deletions, right? So we can say like take the graph A, B, C, D. We can add like a node to A, we can add a node to A, B, whatever. And for the deletions, we can say like let's take off node A, let's take off node B, take off node C, take off node D. What if we pick one of those deletions to be the only deletion we do? Like that is the correct quote unquote deletion. And usually for graphs, we pick lexicographic, like the smallest name of each node to be like the deletion we do. So if we've got a graph with 4 things, A, B, C, D, we'll just always delete A. Like that's the deletion for that graph, is just deleting A, right? If we've got a graph with like B, C, D, E, deleting B is the deletion for that graph, right? So yeah, let's define a canonical labeling for sets. And then let's we'll call that like the sets being in lexicographic order, right? So like I was saying, 1, 2 is like the label for 1, 2, and 2, 1. 1, 2, 3 is the label for 1, 2, 3, 2, 3, 1, 3, 1, 2, you know, all those. And then we'll define the canonical deletion as being just removing the smallest element in the set, right? So the deletion of like, actually, let's look at an example. If we deleted, you know, what's the canonical deletion of 3, 4, 1, 2? Anybody? Yeah.
3, 4, 2.
3, 4, 2, but also we transform it to its like correct labeling, right? Which is 2, 3, 4. But yeah, we just remove the 1, and then that is the only way to like delete quote unquote from that subset. So you can think of like all these augmentations as deletions, right? As like these big sets that are interconnected, right? Like this one might go there, things like that, whatever. Does this diagram sort of make sense? And these bold labelings, we're saying these are the canonical deletions. Like this X3, the only actual deletion it has is this big bold one. And for X4, the only actual deletion it has is this big bold one. And sort of the key thing to notice here is that there's multiple ways to go from X0 to X3 if you took like the augmentations and deletions. There's only one way to go from X0 to X3 or X0 to X4, X0 to X5 if you work backwards from the canonical deletions, right? There's only one path to get there. So if we only move along the canonical deletions, we'll only touch each object once. So this is the algorithm, right? This is the canonical deletion algorithm. It's fairly straightforward. We'll take n to be like the size of the object that we're looking for. And then we'll take x to be the object that we're like augmenting / deleting, so that we're searching over, right? This could be graphs, this could be trees, this could be like some weird other, there's like lots of weird objects in combinatorics. Some of them are useful, some of them aren't. So if it's like if we just know this is not like a solution to look at, we'll just ignore it. This is just like a small optimization. If this is what we're looking for, then we'll output it. And otherwise, what we'll do is we'll get the corresponding, we'll augment the graph, or we'll get the augmentations of the graph, right? At that point, we'll do the local filtering for isomorphisms. Although I don't actually think that's necessary. We'll talk about why. But at that point, we'll do the local filtering for isomorphisms, right? But like we talked about before, that alone isn't enough to search through all the objects. We'll get the corresponding deletion on line 6, which is like, that augmentation also lines up to some other thing's deletion. We'll figure out what that corresponds to, right? So if we go back a little bit, oops. What I'm saying is, we get like the augmentation for X0, we get the deletion that it corresponds to, and then we figure out what object it corresponds to. So on line 7, we've gone from X0 to X1, and we figured out what this thing is and what that thing is along the way, right? Or maybe a better example might be like we've gone from X1 to like this one that isn't necessarily bold, and then from this one it's mapped to a different one, the deletions for X4, right? Essentially, we've got all 3 of these connections. That's what we've got with line 7. That's Y. That's like the object. That's like the next object, basically, right? And then for Y, we compute its canonical deletion. So we have to give it a labeling. That's a slow process, but it's not too bad. And then we have to figure out what its canonical deletion is. And if that deletion is the deletion that we just found, then and only then do we look at this object, right? So yeah, let's look at a specific example, which is we're going to generate graphs with n nodes in them. And we're going to put two restrictions on the graphs. One, the nodes have maximum degree 4. And they have chromatic number at most 3, right? Chromatic number, does everybody know what that is from like 173? That's just basically we're coloring the graphs, with different colors. Why don't you want to do that? I don't know. That does have like genuine applications in like compilers. That's just what I know off the top of my head. Is like you would have something like this if you're trying to like register allocate. Register allocation is a graph coloring problem with like max degrees. But for whatever reason, you're trying to find all the graphs that look like this. So that's how you do it. Is if this delta symbol is the max degree of the graph, if that's greater than 5, then we ignore the graph. If the chirality of the graph, the like amount of not chirality, is that if the amount of like colors we need to color the graph is greater than or equal to 4, we ignore it. And if it's got more than n nodes, we ignore it. That should be a greater than, because if it's got equal to n nodes, we shouldn't ignore that. Part of our solution. And then if it's got all the things we want, then we print that graph out. Otherwise, what we do is we look at every single subset of the vertices. And then we define this v of s to be like a new node, a new vertex being added to the graph that's connected to all those vertices. So this is S is a set, v of s is a vertex that's connected to all of those nodes, right? So we're essentially iterating over like every possible, all the aggregations to this graph. We compute its canonical deletion, and we figure out what like node we'd be deleting if that's the case, right? And then if those are the same vertex, like those are the core, like we're deleting the same thing, then and only then do we go through and look at the next like object that we've created, right? Does that make sense so far? Anybody have any questions about like the algorithm? It's pretty dumb, right? Because all we're doing like 5, 6 extra checks before we like go down an element. So what guarantees do we have when we do this? The main thing is every object we visit only once, right? Which is like, you could do that, without all this complicated stuff, right? You could just like keep a set of all the graphs and do like that isomorphic check that we were talking about earlier. We avoid visiting objects we don't want to, just, by that short circuit. But, any algorithm you make could also have that. The key thing, the really important thing, is that this entire process is completely local. It only depends on the object that you start with. And then every time you branch off of that, you don't need any global state. You don't need to like compare to anything. So you could parallelize this. Actually, the person who I stolen this off from, Derek Stoley, his PhD thesis was creating a software library that lets you essentially lets you write algorithms that operate on graphs, and they just get turned into this form automatically, right? But that was part of his thesis. He did this other things too. So does that make sense so far? All we've proposed is an algorithm to like look at graphs and find, well, graphs, but really just any combinatoric object, and iterate over them, search through all of them, but we can do it in parallel. So let's look at applying this to like an actual open problem in combinatorics, and what kind of results we might get when we do that. So the reconstruction conjecture was posed by Kelly and Ulam, and Ulam was actually one of the scientists who worked on like the atomic bomb. So when they were working on the atomic bomb, they were just like thinking about this problem. There's some papers from like 2022 claiming to have solved this problem, but they're like, one of the authors on the paper is a Yahoo email. Like I don't know how much I trust them. This is one of those problems that is like pretty cool and important in graph theory. It is, unless that paper is an actual proof, still an open problem. So before we talk about like the actual problem, let's talk about graph decks, which is what it's related to. A deck of a graph is essentially the multi-set of all the graphs with the vertex deleted. So basically, if the graph we're looking at is this graph with 4 nodes, we go through and we delete each vertex. We get a graph when we delete that vertex, and that's like a card in the deck. And then all of the vertex deleted cards make up that graph's deck, right? And some of these graphs might be isomorphic to each other, right? Like this graph and that graph are the same thing, even though they come from 2 different deletions, right? And so there's actually 2 versions of reconstruction conjecture. But basically, is that all you need, right? If 2 graphs are isomorphic, they also have the same deck. That's still an open problem in graph theory. Well, maybe. Right? If the two decks are the same, are they the same object? Right? And actually, there's two versions of reconstruction conjecture. One is did I lose it? Okay. One is that we've got the multiple of graphs, which is, you count like this card shows up once, this card shows up once, this card shows up twice. And one is just looking at the set of the cards in the deck. So that would be just like it's like a more stricter version of the reconstruction conjecture where it's like you don't even worry about the fact that this one shows up like a specific number of times. Just from these three alone, you reconstruct, like you check if two things are isomorphic. Does that problem make sense? So this is an open problem. I don't know, math teachers like to say that if you like solve an open problem, you'll make a lot of money. I don't think you'll make a lot of money if you solve this problem, but it's a cool problem. It's got doesn't really have applications. This was like two scientists talking to each other while working on the atomic bomb. It's still cool though. It's an open problem. We don't know if it's true or not. So we could generate every single graph of like an order n and do like pairwise comparisons of equality like we were talking about earlier, right? That's not a lot of programming. If you use Sage before, Sage has a way to like generate all graphs of order n and like enumerate through them efficiently, like as efficient as you can get, basically. And there's software called like GN, things like that. And making the graphs you probably have to do anyway. The issue is that's a lot of comparisons. The reconstruction conjecture has actually been proven for like disconnected graphs. But even if you're looking at connected graphs of order 11, for example, there's about 1 billion graphs. So that's like 1 billion squared comparisons. And those comparisons are also really slow, right? That comparison of like checking if two graphs are equal. That's a lot of comparisons that we have to do. So there's a sort of smarter way to approach this. And this is something that the citation's on one of the other pages, but there's a Brandon McKay who is actually he's the person that created this, like the algorithm that everybody uses to check if two graphs are equal. He sort of explored this algorithm or explored this conjecture and tried to see if he could like brute force find a way to disprove it. And what he realized was that this like talk of deletions that we had and this talk of like the decks are very similar, right? And specifically, if you've got like an n vertex graph to check if it's reconstructible, all you need to do is compare that the augmentations that it comes from, or all you need to do is compare its augmentations to the canonical deletion. So do I have a picture here? No. So does that make sense to people? That took me a little bit to like understand. But basically what he's saying is to go from like an n vertex graph and to show that it can be made from like a deck. All you have to do is compare like the augmentations that come from its deletion, right? So if those deletions match up, if the augmentations of its canonical deletion are all like good, then that graph, you don't have to compare it to anything else, right? Because it can't come from anything else. Does that make sense? Like it's a sort of local search. And so the convenience of this is that, like I said, with the 11 node graphs, there's about 1 billion of those. There's only about 12 million 10 node graphs that are connected. So at every step, you're checking about 100 things instead of checking 11 billion things, right? So in effect, you've gone from n squared comparisons to a like n log n, except it's like log, like it's a much smaller log comparisons. The comparisons are still slow, but you've reduced the amount of comparisons you're doing a lot. Does that make sense? So basically, what we can do is we can generate all the graphs of like say order 10, and then take all of their augmentations, canonical deletion, and then do that comparison, right? I think in practice, like actually doing this, the average came out to be about like 95 comparisons. So 11 billion times 95 as opposed to 11 billion times 11 billion, right? So when he first created the Naughty library, McKay was able to do this for all graphs up to order 11. That was in 1997, right? That was a long, like computers were slow. So the question that I had when I was making this presentation was like, can we do better using modern hardware? And then I Googled if we could. And apparently McKay in 2021 tried this again. And he made a couple other optimizations that he like discovered after 25 years of thinking about a problem. And he was able to show it for orders like 13 graphs, right? So graphs with 13 nodes, if that makes sense. Those are still small graphs, right? Like 13 like, I don't know, I was looking at a friend's graph theory homework and he had like a 20 graph problem, like 20 node graph problem. It's like, we can't even show that this is true for 14 graphs yet. It took him a year and a half of like running on he was running on like a laptop, it looked like from like the description, but like still a year and a half compute time to like go through all order 13. I think that's it. So I wanted to find like, I couldn't find an open problem before. There's computational combinatorics was sort of like deeply explored when computers were first like a thing, like in 1995, 1996. And then people stopped looking into it because it's not really like there's not really much practical use for this. The one like practical use that has been deeply explored and you will make a lot of money if you like look into this is like finding chemicals. But other than that, because chemicals, graphs, you can find like there's like graph theory, combinatoric stuff there. Other than that, combinatorics isn't really like a huge like world-changing thing. But because of that, there's a lot of open problems that like nobody's looked at since 1995. So I couldn't find anything like in the meantime. No Zoom questions. But if anybody has things, I would like genuinely be interested in like applying this sort of approach to on just like a modern computer, find more than what people in 1995 did. That's not it. If anybody has any questions.